You know what mathematicians love? Beautiful equations, elegant solutions, things that work out perfectly on paper with lovely symmetries and surprising connections. And you know what physicists love? Reality. Actual, messy, complicated reality that doesn't care how beautiful your equations are. And wormholes? Wormholes are the perfect example of something that mathematicians find absolutely gorgeous and physicists find absolutely terrifying. See, on paper, wormholes are magnificent. They're solutions to Einstein's equations, real, legitimate mathematical objects that connect two distant points in space through a shortcut. But when you actually ask, could we build one? Could we use one? Could they even exist? The answer that comes back from physics is a resounding, probably not, and if they do exist, you definitely don't want to go near one. Let me show you why. First, let's understand what a wormhole actually is. The technical name is an Einstein-Rosen bridge, named after Einstein and his colleague Nathan Rosen, who first described them mathematically in 1935. Imagine space as a sheet of paper. Now, let's say you want to get from one point on this paper to another point far away. Normally, you'd have to travel across the surface, covering all that distance. But what if you could fold the paper so the 2 points touch, and then punch a hole through both points? Now you got a tunnel, a shortcut through a higher dimension that connects the two locations. That's a wormhole. It's a tunnel through spacetime itself. You enter one mouth, you travel through the throat, and you emerge at the other mouth, potentially billions of light years away, in practically no time at all. Sounds perfect, right? Sounds like exactly what we need for interstellar travel, for exploring the galaxy, maybe even for traveling through time. And here's the beautiful part. This isn't just science fiction. Einstein's general relativity, our best theory of gravity and space-time, actually allows these things mathematically. The equations have solutions that describe wormholes. They're real mathematical objects. But mathematics and physics are not the same thing. Mathematics tells you what's logically consistent. Physics tells you what nature actually does. And the gap between those two things, when it comes to wormholes, is absolutely enormous. Let me walk you through all the ways that wormholes go from mathematical hope to physical nightmare. The first problem with wormholes is the same problem we had with warp drives. You need exotic matter. Matter with negative energy density. Matter that doesn't just curve space-time, but curves it the wrong way. You see, normal matter and energy curve space-time in a way that creates attraction. That's gravity. The Earth curves space-time, and that curvature makes things fall toward the Earth. Black holes curve space-time so severely that nothing can escape. But a wormhole needs to stay open. It needs to have a throat that doesn't collapse. And the only way to keep that throat open, according to the equations, is to thread it with exotic matter that has negative energy density. This exotic matter creates a kind of outward pressure, a repulsive gravity effect, that holds the wormhole open against its natural tendency to collapse. Now, how much exotic matter do we need? The calculations vary depending on the size of the wormhole and how you design it, but we're talking about enormous amounts, mass energy equivalent to planets or stars, or more. And remember, this isn't normal matter that we just haven't collected yet. This is matter with properties that we've never observed in nature. We have quantum effects, like the Casimir effect, that produce tiny amounts of negative energy on microscopic scales for brief moments. But scaling that up to macroscopic amounts, to the quantities needed for a traversable wormhole, we have no idea how to do that. We're not even sure it's possible. The quantum field theory calculations suggest that nature has built-in limits on how much negative energy you can accumulate in any region. These are called quantum inequalities, and they're not just technological barriers. They're fundamental constraints from the laws of quantum mechanics. It's like nature is saying, sure, you can have wormholes mathematically, but if you want to actually build one, you need something I don't provide. Good luck with that. Okay, let's imagine we somehow found this exotic matter. We've got our negative energy. We've threaded it through our wormhole throat. We've opened up this tunnel through space-time. Are we done? Can we start traveling? Not even close. Because now we have the instability problem. A wormhole is not a stable configuration. It's not like a bridge that you build, and it just sits there supporting traffic for decades. A wormhole is more like a soap bubble. It exists in a delicate balance, and the slightest disturbance can pop it. The mathematics shows that wormholes are riddled with instabilities. If any normal matter or energy tries to pass through the wormhole, if any light, any radiation, any particle enters the throat, it can trigger a collapse. And when a wormhole collapses, it doesn't just gently close. It collapses catastrophically, potentially forming a black hole, potentially releasing enormous amounts of energy. And here's the really nasty part. Let's say you want to use the wormhole to travel. You're made of matter. You have mass and energy. The moment you enter the wormhole, your presence disturbs the delicate balance. Your mass energy could be the perturbation that triggers the collapse. So you'd enter the wormhole would start collapsing behind you, and you'd be in a race against the collapse wave. Can you get through to the other side before the throat pinches off? Maybe if you're lucky and if the wormhole is very short. But if the throat is long, if there's any delay, you'd be crushed out of existence as space-time collapses around you. There have been some theoretical proposals to stabilize wormholes. Maybe you could use exotic matter arranged in very specific ways. Maybe you could use some kind of active feedback system that monitors the wormhole and adjusts the exotic matter distribution to counteract instabilities. But all of these ideas require even more exotic matter, even more precise control, even more things that we don't know how to do. Now, here's where things get really weird. Even if we could build a stable wormhole, even if we solve the exotic matter problem and the instability problem, we still have the causality problem. And the causality problem with wormholes is particularly nasty because wormholes don't just let you travel through space. They can let you travel through time. Here's how it works. Imagine you've got a wormhole with two mouths, one on Earth and one near a distant star. Now, take one mouth and accelerate it to very high speed, close to the speed of light, and then bring it back. Because of time dilation, a relativistic effect that Einstein discovered, less time passes for the moving mouth than for the stationary mouth. So now you've got a situation where the two mouths of the wormhole are at the same location in space, but they're at different times. If you go through one mouth, you emerge from the other mouth in the past. You've created a time machine. And once you have a time machine, you can create paradoxes. The famous grandfather paradox, you go back in time and prevent your own birth. Or the information paradox, you receive the blueprint for the time machine from your future self. But where did the information originally come from? Physics hates paradoxes. The universe is consistent. Cause comes before effect, always. The laws of physics work the same way everywhere and at every time. You can't have situations where effects precede causes, where information appears out of nowhere, where contradictions exist. So if wormholes can be turned into time machines, and if time machines create paradoxes, then nature must prevent wormholes from existing, or at least prevent them from being traversable. There's a principle in physics called the chronology protection conjecture, proposed by Stephen Hawking. It says that the laws of physics conspire to prevent time travel and causality violations, and one way they do this is by making wormholes unstable or impossible to create. Whenever you try to build a time machine, quantum effects blow up. Vacuum fluctuations become infinite. The energy density goes to infinity right at the moment when you'd create a closed time-like curve. Nature says, "Nice try, but no." Speaking of quantum effects, let's talk about what quantum mechanics has to say about wormholes. Because general relativity might allow them mathematically, but general relativity isn't the whole story. We also have quantum mechanics, and quantum mechanics has its own opinions. When you have strong gravitational fields, when you curve space-time severely like you do with a wormhole, quantum effects become important. The quantum fields that permeate all of space, the electromagnetic field, the electron field, all the fields in the Standard Model, they all respond to the space-time curvature. And what happens near a wormhole is that quantum vacuum fluctuations get amplified. The curved space-time of the wormhole throat acts like a lens, focusing and amplifying these fluctuations. This creates what's called vacuum polarization and can lead to a buildup of energy called the quantum stress energy. The calculations suggest that this quantum stress energy can become enormous, potentially infinite, and this energy has positive energy density, not negative. So it fights against the exotic matter you're using to hold the wormhole open. It tries to collapse the wormhole. To keep the wormhole open, you'd need even more exotic matter to counteract the quantum effects. But adding more exotic matter changes the geometry, which changes the quantum effects, which means you need even more exotic matter. It's a runaway feedback loop. Some calculations suggest that any attempt to create a traversable wormhole, a wormhole that stays open long enough for something to pass through, would be automatically destroyed by quantum effects. The vacuum fluctuations would blow up right at the moment when you tried to send something through. This is nature's way of protecting causality. This is chronology protection in action. The quantum vacuum itself prevents time machines from forming. Now, I've been talking about all the problems with creating or using wormholes, but what about natural wormholes? What if wormholes formed naturally in the early universe or formed spontaneously due to quantum fluctuations? Could they exist out there somewhere, waiting to be discovered? Here's the thing. We've never seen one. We've never observed any evidence for wormholes anywhere in the universe. If wormholes existed, if they were common, we'd expect to see certain signatures. We'd see gravitational lensing effects that don't match black holes. We'd see matter disappearing into one location and appearing elsewhere. We'd see strange correlations between distant regions of space. We see none of that. Every gravitational anomaly we've observed can be explained by normal matter, dark matter, or black holes. We don't need wormholes to explain any observations. Now, maybe wormholes are just very rare. Maybe they're microscopic, existing only at the Planck scale, far too small to observe. Maybe they exist, but they're not traversable, so matter can't pass through them. But the simplest explanation is that they just don't exist. That the mathematical solutions that allow wormholes are like other mathematical solutions that don't correspond to physical reality. Just because you can write down an equation doesn't mean nature uses that solution. Let's talk about practical issues. Suppose, miraculously, we solved all the other problems. We found exotic matter, we stabilized the wormhole, we prevented causality violations, we dealt with quantum effects. Now we want to actually use this wormhole to travel. What would that be like? First, the size. To make a wormhole big enough for a human to pass through comfortably, you'd need the throat to be at least, say, a meter in diameter. The amount of exotic matter required scales with the size. Bigger wormhole, more exotic matter, much more. And then there's the throat length. How long is the journey through the wormhole? Some solutions have arbitrarily short throats. You step in one end and immediately step out the other. But other solutions have throats that could be quite long. You might spend hours or days traveling through the wormhole throat, and during that entire time, you're in one of the most extreme environments imaginable. The gravitational tidal forces near a wormhole throat could be enormous. Remember, you're in a region where spacetime is severely curved, where the exotic matter is creating bizarre gravitational effects. Depending on the exact geometry, the tidal forces could tear you apart. Your head could experience different gravitational acceleration than your feet, stretching you like spaghetti. This is the same problem you have with black holes. It's called spaghettification. And unless your wormhole is very carefully designed, very large, with very specific exotic matter distribution, you'd be spaghettified during the journey. Oh, and I haven't even mentioned what you'd see. The light traveling through a wormhole would be bent and distorted in bizarre ways. You might see the exit while you're still at the entrance. You might see multiple images of yourself. The visual experience would be completely disorienting and potentially nausea-inducing. So why is there such a gap between the mathematical hope and the physical nightmare? Why does mathematics allow wormholes but physics make them seem impossible? Because mathematics is about logical consistency. If you can write down equations that don't contradict themselves, that's a valid mathematical object. Mathematics explores all possibilities, all logical structures, whether they correspond to reality or not. Physics is more constrained. Physics has to match observations. Physics has to respect not just general relativity, but also quantum mechanics, thermodynamics, causality, every other principle we've discovered about how nature actually works. And when you take all of those principles together, when you look at the complete picture, wormholes start looking less and less plausible. They're allowed by one piece of physics, general relativity, but they're constrained or forbidden by other pieces, quantum mechanics and causality. It's like finding a building design that works structurally, but violates the fire code, the electrical code, the plumbing code, and the zoning laws. Sure, structurally it's sound, but you're still not going to build it. Wormholes are mathematically sound. They're solutions to Einstein's equations. They're logically consistent within the framework of classical general relativity. But when you add in everything else we know about physics, they become problematic, possibly impossible. Does this mean wormholes definitely don't exist? No. Science doesn't deal in absolute certainty. Maybe there's some aspect of physics we don't understand yet. Maybe when we finally develop a complete theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, maybe that theory will have something to say about wormholes that we haven't figured out yet. Maybe quantum gravity will make wormholes easier, or maybe it'll make them completely impossible. We don't know yet. But based on everything we currently understand, wormholes are a mathematical curiosity, not a practical technology. They're a beautiful solution to Einstein's equations, but they require exotic matter we can't find. They're unstable in ways we can't control. They create causality problems we can't resolve, and they're destroyed by quantum effects we can't prevent. They're a hope on paper, but in the real world, in actual physics with all its constraints and complications, they're a nightmare. And you know what? That's okay. That's how science works. We explore ideas mathematically, we see what's possible in principle, and then we ask whether nature actually does that. Sometimes the answer is yes, sometimes it's no, and sometimes it's maybe, but not in any way you'd find useful. Wormholes fall into that last category. Beautiful mathematics, probably impossible physics. And honestly, I think that's fascinating. The fact that nature is more restrictive than mathematics, that the real universe is more subtle and more constrained than pure logic would suggest. That tells us something deep about reality itself. The universe isn't just any old solution to equations. It's a very specific solution, with very specific properties, governed by principles that go beyond mere mathematical consistency. And understanding why wormholes don't work? That's just as important as understanding what does work. That's physics. Thank you.